Hi everyone, and welcome to your Lactate Threshold video lecture. This one is fairly short, but also really important. So it's a key component of physiological testing and ultimately illustrates where the crossing between aerobic and anaerobic activity takes place. One of the more common places that this measure is taken is during our graded exercise testing, or if you think about your cardiovascular tests where you incrementally increase the difficulty, as we spoke about in the endurance testing lecture. We will find that the lactate threshold is an important component of that and is built kind of into it, even though, as we'll come to find, it's related to anaerobic activity. Okay. So an overview of what lactate threshold is the point when blood lactate shows a nonlinear shift upward. Okay, so we're measuring lactate in the blood, and usually this is done through either, it kind of looks like a blood glucose monitoring thing, but you take a little bit of like a pinprick to the end of the finger. Sometimes it's done in other places, but most commonly fingertips, and take a little drop of blood into the machine. It'll read the blood lactate. And so when you're exercising incrementally and increasing that intensity, there will be a point at which, instead of slowly continually increasing, you'll see an upward shift with that. And there's actually a couple of them that we can look at. So in untrained individuals, we'll see that this happens around 50% of someone's VO2 max. So it happens quite early on. And in athletes, we'll notice this lactate threshold occurs closer to 80%, sometimes up to 90% of their VO2 max. Now, 90% would be very well-trained individuals, whereas 80% would be more common for a hobbyist endurance athlete, okay? Now, what is the cause of this? Well, ultimately what happens is as we increase our workload, we know that we'll take a shift from our fatty acid based metabolism or our aerobic based metabolism, because again, that's that slow, low intensity, long duration or fatigue resistant muscle fiber types that we're using for that. And as we shift away from that lower intensity and start getting to a higher intensity, our body starts needing to recruit more and more fast twitch muscle fibers, which means we need to recruit more and more of our anaerobic system. Now, if you recall, that anaerobic system uses carbohydrates to be able to produce the energy, the increasing energy demand for type 2 muscle fibers that we need through carbohydrates, right? Carbohydrates is our jet fuel, right? So, so through the stimulation of our sympathetic nervous system or our fight or flight system, we get this increased type 2 or fast twitch muscle fiber recruitment, which means more carbohydrate use. And so when that happens, we reach this point where within our cell, because our energy demands aren't being made through aerobic metabolism, we need to start adding on some anaerobic energy as well. And what will happen is this backlogging or accumulation of lactate starts to occur intracellularly, so within the cell. And then it gets to a point where it can no longer stay there, gets into the blood, and we start seeing accumulation in blood, okay? So it's, again, once lactate reaches the blood, that's when we start measuring it. And so when we do that, we see a response like this. So oxygen uptake, another way you can view that axis here on the graph is workload. So as we increase our workload or our ventilatory rate or the amount of oxygen we're using in order to try to produce our ATP, we'll notice that the blood lactate volume increases. So this is millimoles. Moles, if you've ever done chemistry, you'll know what it is, but it's just a certain unit of measure saying we have this many atoms of a certain chemical. And if you've heard of Avogadro's number, that's what it is, per liters of blood. And so again, as we increase our workload, we reach this point where we get to about 2.5 millimoles per liter. And that's sometimes a preset number that clinicians will work with. And once we get to that point, we see this linear response to the workload all of a sudden shift upward. Okay, so it's at that influx where we get that increase or accumulation of lactic acid in the blood. Now, just a side note and a reminder, although I'm sure you all caught it and remember from the first time we had a discussion about lactate threshold, but the things that cause muscle fatigue and soreness and all of that is not lactic acid. In fact, lactate is like the sponge to help prevent that issue. So as we're accumulating more, yes, that is related to this tipping point of workload where we go into our anaerobic capacity, and therefore we don't last very long on the other side of our lactate threshold because we're starting this accumulation or backlog. And the reason for that, as it gets higher and higher, is again, we run out of sponges in order to sop up hydrogen protons. That is what we've come to find is the root of a shift in the pH of our cells and our working muscles that cause them to fatigue, so they don't work as well as cause that discomfort and nauseous feeling that we typically associate with extremely challenging exercise. Okay, if we're to look at the same, a similar thing, if we're looking purely at ventilation, so here we have a running speed that increases over time. Again, it's just an increasing workload. That's our measure here. We will notice that our ventilatory rate, so our breathing rate, as we go along, will respond linearly to this until we hit this point. So this is our ventilatory threshold. So if you recall, when you do a VT1 test, this rate where your breathing starts to increase even just a little bit, and again, in untrained individuals would be around 50% of their VO2 effort. Trained individuals be 80 to 90. 85 is pretty common. And yeah, so we'll see that drastic increase in ventilation. So here you can still speak fairly well. This is just where it barely starts getting a little challenging to speak. You would maybe take an extra slightly deep breath in and then notice just a slight pause. If you're like really out of breath, huffing and puffing, your ventilatory rate is way up and you're well beyond your VT1. So that's why it was so important when you're doing that test to slowly and incrementally increase that workload, let your body catch up to that workload by hitting steady state before you get to that point where all of a sudden, because now a little bit, we'd expect our continued ventilation to be here, and if we increase the workload a bit, but all of a sudden it jumps up, and again, that's where we know our VT1 is, okay? Now, that is the gist and the premise, but I wanted to speak a little bit more detail about this because it is really, really important, again, especially with graded testing. I went and found a few more graphs here just to illustrate how this effect occurs for some. So this graph is got a few things going on. We'll start with the bottom. So this is power. Remember, that's work over time. And one of the most common ways that we measure that on the bike is through watts. Okay, that is the unit of measure. So we have our watts down here, and we notice that we have an increasing workload as we go from left to right. On the left y-axis here, we have a heart rate starting at 60, so common resting heart rate, going up to 180, which would be pretty top end for most individuals exercising. And then here we have a lactate. Okay, again, 0 to 4 being the really important indicators, and then 6, 8, 10. So let's take a look what's going on. The blue lines, what they represent is a early season training individual or someone at a baseline test, so the first measure they do. And we can notice here that is higher in heart rate for the same, if we're just going to look at these lines here, sorry, this is heart rate. So if we look at the power as it increases in this workload, say from 180 to 300 watts, we notice this nice linear relationship to the workload, steadily increasing and correlating to that, okay? So we notice that every time we increase the workload, the heart rate goes up. We'd expect that, okay? So we'll, again, just looking at the blue line. So this is, say, like a test done in September of some year. Okay, so we this increase, with, let's say, 6 months of training. So now we're in spring, let's say March or April, let's say March. And now for this exact same workload, we do this test again. It's a graduated or a gradual increasing aerobic test here. It's slowly increasing the power. We notice that for the same amount of work at, say, 180 or 300 watts, that the now more trained individual is lower in their heart rate that they have for that given workload. And this makes sense, right? The more trained we are, the better response cardiovascularly we have to exercise. We know this, right? So when we take that same training adaptation with our lactate in consideration, we'll notice as we increase over time that we lower the accumulation of lactate in our blood for longer. So again, if we take a look at 180 watts, we notice that our trained individual in spring versus when they were at baseline drops significantly for the same amount of work. So we produce less lactate. So what does that show? These trained individuals can stay in their aerobic workload longer. And so that's good because, again, once you hit lactate threshold somewhere around 2.5, so right here at about 330 watts in our more trained individual, and it was at 270 when they hit it roughly when they're less trained. Okay, so that's a pretty big difference in our lactate threshold there, right? So as we see this influx now at 330, that means this person is doing, let's see, 30, 50 watts more work before they hit threshold. That is very significant. That's a very significant difference in watts for most individuals. So again, that's the advantage to training and what we would expect to see with their heart rate, increasing workload, and lactate threshold, and how that would shift, okay? Very similar graph here that just helps tie in a few similar concepts. So here we have our ventilatory rate, we have oxygen consumption, and our blood lactate. So again, we'd probably, if we had heart rate on here, just be linear, kind of, again, steady, increasing linear here. But we notice as we increase our workload, again, oxygen consumption is like VO. This is just there. We have our point of lactate threshold, which we've been talking about, which again is roughly, we can say around 2-ish. This graph represents it a little differently. But you'll also notice something called point of OBLA. So that's onset of blood lactate accumulation. Now that's higher, and that's usually set at 4. And that's used in a few different settings, just as a standardized rate of when we consider lactate threshold to not only have been crossed, but we see with certainty an accumulation of lactate in blood, right? At this level, maybe if we get an artifact up high, it comes back down, or we're not quite into our anaerobic threshold, right into our anaerobic system at 2.5, but we'll know for sure once we get to 4 millimoles per liter, okay? And we can also mark that kind of as our ventilatory threshold 1. So again, we've just left our aerobic zone. We are now in a crossover point where both the aerobic and anaerobic systems are working quite readily. But once we hit this 4, we hit respiratory compensation, and that's our VT2, or our ventilatory threshold 2. When we hit that, we are for certain in our anaerobic zone, predominantly using that as our main source of ATP, and we have a very limited amount of time here in this work zone. So if you want to relate that to a car analogy, again, you've hit the red line, you're past the red line, and now you have a limited amount of time before the engine blows up. Okay, within this space here, you definitely have a little bit more freedom. This is like yellow zone, and this is very fatigue resistant down here. Okay, let's take a look here to that point. So a lot of you some of you managed to get the question as far as how do we use lactate or VT1 for trainability or setting up an exercise program for someone. Well, quite simply, this gives us our lactate threshold 1, our ventilatory threshold 2. We can do that with blood lactate as well, like this graph has, and we can create 3 zones of work. Okay, we have our zone 1, which will be aerobic work. So if we want to work on someone's aerobic training, we can look there. Zone 2 is this crossover point where it is a blend between aerobic and anaerobic work. You can call it threshold or anaerobic threshold zone if you wish, because at the end of that zone, so slightly up here would be close to 4 millimoles, down here is 2.5 millimoles. As far as our lactate thresholds would be, and then anything above, again, that 4 millimoles per liter of blood lactate is our anaerobic zone. So for sure, limited time here, lots of carbohydrate use. Here, all primarily fat, if not all fat use for our aerobic metabolism. Okay, so just one more way to kind of look at that. What is also common in training and exercise fitness prescription these days, other than a 3-zone model, would be a 5-zone model. And the way that works is we have our aerobic, and I'm sorry, this is a little blurry. I'll do my best to explain. There we go. Let's center that a bit more. So we have our ventilatory rate is what we're measuring here. But as we know now, our blood lactate follows a similar pattern. So within our first amount of workload here, or our kind of zone 1, we see that right in the middle of this zone 2. So 1, 2, 3, 4, 5. Right in the middle of zone 2, we have our aerobic threshold. So just above that and just below would be just above and below our VT1, or we could also say our LT1. As we get into this middle zone, this is a tempo, and this would correlate with this inflection here. This would be our anaerobic threshold. So this would be zone 4. Just above it would be above our 4 millimoles per liter of our LT2. Just below would be just below that. Okay, so again, once we're up here, we have a very limited amount of time before we hit our VO2 max, and usually people will voluntarily decide to end their test at that point in time. Okay, so lots to digest there, but a really great tie-in from a number of different sources. For example, a lot of lab material was covered in that lecture. A lot of ideas as far as different types of metabolism was tied into that lecture. And definitely, if I would suggest reviewing this lecture a few times to make sure you get these concepts. It also gives you a great foundation as to how to go about prescribing exercise for people. Because we can set up these zones, we know exactly when they're going to be training, let's say in a aerobic zone versus a crossover zone versus an anaerobic zone. Okay, and maybe just to clarify that even slightly as well. So to train an individual, when you start working with them, you start primarily in zone 1. Once they're able to handle that workload fairly readily, adaptation takes a few weeks, but every individual is slightly different. Then you can start introducing intervals. With intervals, you increase the length of the intervals. You essentially have people go from zone 1 into zone 2 and back to zone 1. So let's say like 5 minutes, 3 to 5 minutes in zone 1, 3 minutes in zone 2, back to 3 to 5 minutes in zone 1, and etc. for their duration of their exercise, half hour, whatever they've been able to build up to. Okay, once people feel comfortable and you notice that their zone 2 target has kind of become a bit easy, then what you can do is start training into intervals that go from zone 2 to zone 3. Okay, you kind of alternate between there. And then you can get tempo zones where you spend an entire bout of exercise in zone 2, going back to some build up to zone 3 exercise. But ideally, you do not have a new client or someone that you're working with. Do a lot of zone 3, or in this case, zone 4/5 intervals, unless you know they've demonstrated this before to you through maybe previous exercise. Okay. Okay, so yeah, again, go ahead, review as needed. Lots of tie-ins here. And yeah, thanks for watching.